So I will talk about the hypoelliptic Laplacian. So to say it in words, what I will explain is a construction of an object which interpolates between two kinds of well-known differential operators. One is a standard Laplacian on a manifold, on a Riemannian manifold, and the other is a vector field which is the generator of the geodesic flow. So this is an interpolation between two kinds of objects which in principle are unrelated. In particular, as differential operators, they don't act on the same space. So interpolating between two kinds of objects as different just really does not make sense a priori. There is a dynamical aspect to this, a dynamical counterpart, which is an interpolation between two sorts of dynamics. Oh, this is okay. The first dynamic is a Brownian motion, which is as erratic a motion as possible. And the other one is a geodesic flow. Geodesics, you know, they are like straight lines. They are as regular as possible. And the fact this interpolation exists is remarkable in the sense that in spite of the fact that the interpolation takes place between two completely different sort of objects, they are basic conserved quantities, in spite of the fact that we interpolate between two kinds of objects. So here is a summary of the talk, but I will immediately go to the description of what the hypoelliptic Laplacian is supposed to do. So Laplacian and geodesic flow. So I give myself X to be a Riemannian manifold. So if you like better, think for the moment just as Rn to be the Euclidean space. So it's a generalization on a Riemannian manifold, you have the notion of distance and metrics. And let me call X script the total space of the tangent bundle. So I have the base manifold, and over the base manifold, I add these tangent fibers, Tx. So this space is of dimension 2n, so you double the dimension. And then on the base manifold X, I introduce delta X, which is the so-called Laplace-Beltrami operator acting on X, which is a generalization of the classical Laplacian. So I also introduce Z, which is a geodesic flow. So in this case, for the moment, I will just say that it is a vector field, not on the base manifold X, but on the total space X script, on the bigger space. So in particular, if you integrate the trajectories of this vector field of X script and you project them down on the base manifold, what you get are the geodesics on the manifold X, the solutions of the second order differential equation x double dot equals 0. So what is a main statement? So again, X a Riemannian manifold, delta X the Laplace-Beltrami operator, and Z the generator of geodesic flow. So the main statement says there is a canonical family of hypoelliptic operators LBX. I will explain all the words. Acting on a bigger space X script, the total space of Tx, that interpolates between a scaled version of the Laplacian and a scaled version of the geodesic flow. So canonical family here means that there is no choice. And the fact these operators are hypoelliptic, that means that for an analyst, they are almost as good as elliptic. So for an analyst, they are good operators, good partial differential operators, which are the elliptic ones, which are essentially the locally invertible ones, those whose principal symbol circle is invertible. Hypoelliptic is fancier. They are less obviously good, but ultimately they turn out to be as good. So let me just explain now the dynamical counterpart. As I said before, so for B positive, I consider the second order differential equation, which is written on the board. The right-hand side here is W dot, which is so-called white noise. So that's a second-order differential equation which is excited by extremely random shocks. This equation is known in mathematical physics as the Langevin equation. And so the dynamical counterpart is there is an interpolation of dynamical systems. So I wrote here the interpolation between, for b equals 0, that's Brownian motion. In some sense, in this equation, you make b equals 0, you get the classical Brownian motion on the manifold. That's as random as possible trajectory. It is extremely non-smooth, nowhere differentiable, and so on. And for b equals infinity, you just get exactly the equation of geodesics. Now, this interpolation is the dynamical counterpart to the interpolation between the Laplacian and the geodesic flow through this family of operators LBX. So what is the hypoelliptic Laplacian good for? So the first property of this deformation is that in spite of the fact that the deformation takes place through extremely different families of operators, still they are conserved quantities. So this is really counterintuitive. On a certain class of manifold, on a certain class of geometries, actually the full spectrum of the operator may be conserved. So the deformation connects also two completely different kinds of dynamics. And so I will now explain how does the operator LBX look like. How does it look like? So again, I take the manifold X with the total space X script of the tangent bundle. So the generic point of this manifold X script is little x, y, where X is in the base manifold and y is a vertical point. It's a generic point in the tangent bundle. So I introduce a first operator. That's an operator which just differentiates in the fiber direction. That's an extremely well-known operator in mathematical physics. That's a so-called harmonic oscillator along the fiber. So I wrote here in one form, so minus delta tx is just a Laplacian in the vertical direction. Norm of y square is just a Riemannian norm of the generic point y in the fiber, and n is a dimension. On the other hand, I introduce a new operator, which is now z, the generator of the geodesic flow. So this is a vector field on this manifold X script, and I wrote here it in local geodesic coordinates. So you can think of this vector field as essentially being the sum of yi d over dxi. So, of course, this is not an intrinsic way of writing, but roughly speaking, you can think of it this way. And so the hypoelliptic Laplacian, typically it's a weighted combination of these two kinds of operator, the weight 1 over b squared appearing in front of h and the weight 1 over b in front of z. And then there are extra geometric terms which are extremely important for the success of the theory, but for the moment, from an operator theoretic point of view, I will omit them. So, as you see, the operator is obviously, first of all, it's absolutely not visually a deformation of the geodesic flow. If you make b tend to 0, you will not see, a deformation of the Laplacian. As b tend to 0, this operator does not obviously deform the Laplacian on the base. Such an operator is known in the context of statistical physics as a Fokker-Planck operator. It is non-self-adjoint because the vector field z is non-self-adjoint. It is non-elliptic because it just essentially differentiates twice in the fiber direction, but just once in the base direction. So it is hypoelliptic, so it is a nice operator from the analyst's point of view. In particular, it has a heat kernel. This had been actually, in some sense, a remark made by Kolmogorov in 1934. So how is it constructed? So I should say, how is it obtained? My talk will not center on this aspect, but I would say that the construction of the geometric hypoelliptic Laplacian is determined by the considered geometries. I put here geometries in the plural. There is not only one hypoelliptic such an operator, there are several determined by the considered geometries you look at. The hypoelliptic Laplacian, to be effective, that is to have all these wonderful properties, is in general a non-scalar operator. So in spite of the fact that you may start from a scalar Laplacian, in general to have the good properties of this operator, hypoelliptic Laplacian, it is non-scalar. In the context of de Rham theory, its geometric construction involves a symplectic form on the total space F script of the cotangent bundle, I would say. So I will not at all describe this here, but let me tell that effectively, in some sense, the new ingredient with respect to the classical construction of the Laplacian is the incorporation of the symplectic form. Now, let me give a picture. So that's a typical mathematician picture. So I wrote here the base manifold X. I wrote the fiber Y, the fiber Tx with generic element Y in Tx. Along the fiber, there is acting the harmonic oscillator. And I also wrote this vector field, which essentially differentiates in the base direction z sum of yi d over dxi. So let me now explain simply why does such an operator deform the original Laplacian as b tends to 0. So again, X a compact Riemannian manifold, and I introduce this operator LBX now, which is a combination of the harmonic oscillator and of the geodesic floor. So the harmonic oscillator itself, it's well known that a self-adjoint non-negative operator, that its spectrum is discrete, it's the integers, and in particular, its kernel, its fiber-wise kernel, is one-dimensional and is spanned by the Gaussian function. Now, the remarkable fact about the geodesic floor, the vector field z, is that it is odd in the variable y, as you see. So when acting on a Gaussian, it maps the Gaussian into its orthogonal. It's into its L2 orthogonal. So this means that I can write the operator LBX as a matrix. As a matrix simply by splitting the total L2 space into the kernel of H and its orthogonal. And so I wrote it as a 2 by 2 matrix. The first line or the first column is just the kernel of H, and there is no element in this column because, again, Z maps the kernel of H in its orthogonal, and H vanishes on its kernel. So this is the matrix structure of LBX with respect to this splitting. So what we will do is pretend that LBX is just a finite dimensional matrix. Forget about this as being differential operators. Let's take H to be a finite dimensional matrix, non-negative, whose kernel is one-dimensional, and having this structure. So we will pretend this for the moment. So let me explain the collapsing of LBX to the original Laplacian. So what we will do is instead study the resolvent of the matrix here. Study the resolvent as b tend to 0. So in fact, we will try to compute the inverse of lambda minus LBX as b tend to 0. And you will just use classical linear algebra to do this. And if you do that, you find that if P is the orthogonal projector on the kernel of H, then the resolvent of LBX converges to actually an operator which just acts on the kernel of H, and which is the resolvent itself of a new operator, which is given by P, Z, H minus 1, Z, P. The fact that the inverse of a matrix is nonlinear in its coefficients and even is quadratic is well known, and hence the appearance of these P, Z, H minus 1, Z, P. Now, in our case, what is the kernel of the harmonic oscillator? I told you these are functions which are Gaussian along the fiber. But functions which are Gaussian along the fiber, they come from the base. So the kernel of H can be identified with functions on the base x. That's just a smooth functions on x. And now, if in our case you just do this elementary computation, you find that p z h minus 1 z p is given by half of the Laplacian. In particular, this formula explains why we get an operator of order 2 on the base, while the vector field z was of order 1. So in some sense, it is true that the resolvent of LBX converges in the proper sense to the resolvent of the Laplacian on the base by a collapsing. By this collapsing means that you forget about the fiber except for the kernel of the harmonic oscillator. Now, let me briefly explain the convergence of heat kernels as B tends to 0. So again, X is now a compact or non-compact with uniform geometry. So the first thing is that I told you these operators LBX do have heat kernels. It's a bit strange because they are not elliptic, still they have heat kernels. And the first fact is that these heat kernels are now in the variables x, y. So you have q, b, t, x of x, y, x prime, y prime. That's a kernel in the big space. So it verifies when b remains bounded, it verifies uniform bounds in the variable b. And the uniform bounds say that essentially it has a Gaussian decay when the points x and x prime are far apart, and when also y and y prime are big. And the second thing is that the hypoelliptic heat kernel, this heat kernel in the big space, when b tends to 0, in some sense converges to the heat kernel on the base manifold, this ptx of x and x prime. There is just these extra factors, exponential or minus 1/2 of y squared plus y prime squared. Now, let me briefly explain what is a geometric Langevin process. So now we're going to move to the dynamical aspects of the interpolation. So the stochastic process corresponding to the hypoelliptic Laplacian is a geometric Langevin process. Well, indeed, I rewrote this hypoelliptic operator LBX in a slightly different form by conjugating it by the Gaussian function, so that instead of having the potential y squared minus n, you have now twice radial differentiation, vertical direction. And so it is well known that the dynamics, there is a second order operator, there is a corresponding stochastic differential equation corresponding to this operator. This, I wrote it here, and this dynamics projects to the Langevin equation big square x double dot equal minus x dot plus w dot. So this dynamics is a C1. Contrary to when b is non-zero, the dynamics is C1 in time t. It is a process X is a process whose speed essentially is a so-called Ornstein-Uhlenbeck process. So again, from a formal point of view, if you just look at the equation, you find that when b is equal to 0, you get Brownian motion. When b is equal to infinity, you get the geodesics, x double dot equals 0. However, this is just an algebraic argument. So let me now give more precise properties of these processes x, y as b tend to 0. So as b tend to 0 then, it is true that the probability law, so if you just look at the projected trajectories x, which now depends on the parameter b, if you look at the projected trajectory as b tend to 0, it converges in the proper sense to Brownian motion. Now, if you just look at sample the speed at times t1, t2, tm, by scaling the speed by the parameter b. So, in principle, the speed explodes because you converge to Brownian motion. However, let's scale the speed by b. So what you find is that these scaled speeds converge as b tend to 0 to a product of independent Gaussians of variance 1/2. And finally, this is even stranger. If you just look at the joint law of this hypoelliptic diffusion and the sample speeds, they converge to the product law. That is, in some sense, the scale speeds become independent of Brownian motion itself. So this is typically a phenomenon that's infinite dimensional. That cannot happen in a general situation. And finally, this is even probably stranger that the proper version of the energy of this hypoelliptic diffusion converges to something which is deterministic, which is T/2. That's, as we shall see later on, that's a manifestation of the conservation of energy. So all these sort of statements are a geometric form of a well-known phenomenon in statistical physics, which is homogenization. Now, let me approach the hypoelliptic theory from the variational point of view. So I will introduce an action functional. So I will look at loops. I will just limit myself not to paths, but to loops. Loops which are parameterized by 0t. So if you take t equals 1, that's just parameterization by the circle. So I consider such loops. And I introduce an action functional that's a functional of given loop, which is essentially, if you look on the right-hand side, that's a deformation of the so-called classical energy of the loop. So in general, if you have a path, you know what its physical energy is, that the integral of x dot square, of the norm of x dot square. So I just perturb this energy by introduce b to the fourth x double dot square. So in particular, for b equals 0, we recover the energy. So what is the point about this energy here? Well, it is because from a formal point of view, okay, from a mathematical physicist point of view, what is the measure on the path space, or in this case on the loop space, corresponding to the hypoelliptic Laplacian? It is exactly given by the exponential of minus ebtx dx. This is a formal way of representing the measure associated with the hypoelliptic diffusion in some sense, as given by having a density, which is given by the exponential of an minus ibt of x dx. So actually, for b equals 0, it's a well-known representation of Brownian motion itself as just being, or Brownian measure as being a measure whose density is given by the exponential of minus the energy. So from a formal point of view, because ibt deforms the energy, it's fairly obvious that this measure dqbt should deform the Brownian measure. But also, this tells us something more, that as b tends to infinity now, this is something that we've not yet talked about, as b tends to infinity, if you look at the action gets extremely big when b tends to infinity, except when x double dot is equal to 0. So that indicates that when b tends to infinity, this measure should concentrate on the geodesics. So this already tells us that our differential operator itself, the operator LBX, should have something to do with the geodesic flow when b tends to infinity. So let me go into more details from a geometric point of view. Let me introduce the notion of pseudo-distance. So once you have the energy, as is well known from the energy of passes, this is a canonical way of defining the Riemannian distance of a manifold. You define the square of the distance in some sense as being given by the minimum of the energy of a path connecting 2 points. So with this new action, which is IBT, you can actually fix origin points x, y over b. I take this special scaling, and endpoints at time t, x prime, y prime over b, and define again the minimum of the energy given by this new action functional. So if you do that, you define hbt again of xy, x prime, y prime to be the inf of this new energy. So this inf actually does not define a distance. This is very easily to check because in particular on the origin it does not vanish. So the underlying geometry is completely different from a Riemannian geometry. However, let's look at the case of x equals Rn. So on Rn, you can compute explicitly, the minimum of the action explicitly. You have explicit formulas. And so what you find is the following thing. First of all, it is that the hypoelliptic heat kernel is essentially given by the exponential of minus the minimum of the action. So exactly like in the case of the scalar case, for scalar heat kernel, you get the heat kernel, classical heat kernel, being given by the exponential of minus x prime minus x squared divided by 2t. Here you replace this distance square by the minimum of the action. Exactly. So this is because actually the processes we deal with are Gaussian. And so all the approximation, pseudo-approximation we get by these functional integrals are exact. And also what you find is that the minimum of the action when b tends to 0, in spite of the fact that the action itself deforms the original energy, the minimum of the action does not converge when b tends to 0 to the classical minimum of the energy on the base, which is x prime minus x squared divided by 2t, but there is the extra term, 1/2 of norm of y squared plus y prime squared. This is a phenomenon called gamma convergence that I will not explain. The fact that the minima do not converge, the minima of an action when b, the parameter tends to 0, does not converge to the minimum of the limit. There is an extra term. And of course, this is perfectly compatible with what I mentioned before, that when b tends to 0, the heat kernel should converge to the classical heat kernel on the base with a correction, which is precisely half of y squared plus y prime squared. Now let me go to the case of S1. Now we will see conserved quantities. So first of all, I consider again now the harmonic oscillator in one variable, half of minus d squared over dy squared plus y squared minus 1. That's the harmonic oscillator. So it is well known that this is a self-adjoint elliptic operator, which is non-negative, and its spectrum is discrete. It is given by the integers. So in particular, its kernel is spanned by the Gaussian function, and more generally, its eigenfunctions, they are very easy to compute. Actually, this was a computation done by physicists at the beginning of the class quantum mechanics. The eigenfunctions are just polynomials factored by the Gaussian function. The polynomials pk are the so-called Hermite polynomials. And all these functions, the Gaussian or Hermite polynomials, they are not only smooth in the variable y, they are analytic. So this will play an important role to understand the properties of this hypoelliptic Laplacian. So I again take the operator LB. That's the hypoelliptic Laplacian with over S1. That is, here I take x in the circle and y to be just a variable in R. So that's the simplest hypoelliptic Laplacian as possible. So what we shall do is sort of make a reduction of squares. To understand this operator better, we'll make a reduction of squares which consists in putting together y squared minus y over b d over dx. So this is what we obtain here. And then what we will try to do is try to say, can we make in this operator a translation of the coordinate y by the operator b d over dx? That is, can we translate y into y plus b d over dx? So, of course, this is not permitted because you cannot a priori translate a coordinate by an operator. If you just think in Fourier transform terms, if you just look Fourier transform in the variable x, what this would mean would be that you translate the coordinate y in the imaginary direction. You would just make y gives y plus I big psi, which is again, from the point of view of theory of differential operators, is not permitted. But actually, why do we want to do this? So I will just explain that just translation, making a translation in this case, means that we want to conjugate properly the operator LB. So let me explain this conjugation. So I introduce a cross derivative operator, d squared dx dy, which is a so-called hyperbolic operator. So in particular, it doesn't have a heat kernel. This operator, contrary to the Laplacian, this is a very bad operator from the analysis point of view. It doesn't have a heat operator. However, what I meant by the conjugation before is that if this conjugation made sense, I would say that the original LB, the original hypoelliptic operator, would be conjugate by this badly defined e to the bm to another operator on the right-hand side, which is much better now, which is just an operator in which the coordinates x and y have separated, and besides, the operator on the right-hand side is itself self-adjoint, and it is now elliptic. Now, the problem of this conjugation is that it only makes sense from an algebraic point of view. Analytically, it does not make any sense. However, if the conjugation could be made sense of, that would say that the operator LB would be conjugate to the operator on the right-hand side, and this would make the two operators isospectral. That's a very important information. So the point about this formula is that the conjugating operator does not make any sense. So in some sense, the conjugation is legitimate. It's because, well, I mentioned before that this conjugation was equivalent to translating y in the imaginary direction. But such translations are authorized in our case because precisely the eigenfunctions of the harmonic oscillator are analytic. And so indeed, you can, on these ones, make such an imaginary translations. And so ultimately, the operator LB, our original operator, can be explicitly diagonalized. So it's on a very distorted base with respect to the classical Hermite polynomials, or in the case of the Laplacian, Fourier exponentials, very distorted base in the sense that the operator, again, which maps a base of eigenvectors to the other base of eigenvectors, is extremely non-bounded. So what is a spectrum of LB? So I rewrote again the operator in two variables, x and y. And now what I know is that the spectrum of LB is made of two pieces. I mean, the plus here means that you add these elements of these sets term by term. So there is a first piece, which is just 2 chi-squared p squared, that's the spectrum of the Laplacian on S1. And then there is a scaled version of the integers n divided by b squared. So that you see that, first of all, the spectrum remains real, in spite of the fact that LB is non-self-adjoint, but also that there is a part of the spectrum which does not depend on b. That is, if this integer in n over b squared, you make the integer equal to 0, you find that in effect the set 2 chi-squared p pi squared, which is a spectrum of the Laplacian on S1, remains rigidly embedded in the spectrum of LB. So it is not the spectrum of LB is equal to the spectrum of base Laplacian. It is that the spectrum of Laplacian is included in the spectrum of LB. So I will not explain by an algebraic trick how to recover the spectrum of the Laplacian on S1 from the spectrum of LB. But before that, let us observe that as b tends to 0, the spectrum of LB, so all this n over b squared, they all go to infinity as b tends to 0, except for the 0 integer. So in the proper sense, from a spectral point of view, we see that the spectrum of LB converges in the proper sense to the spectrum of the Laplacian on S1, which again makes good sense of the fact that LB should be thought of as deforming the Laplacian on S1. So the operator LB as b tends to infinity. Now, by rescaling the coordinate y, what you find is that as b tends to infinity, the operator LB looks more and more like the geodesic flow. So in some sense, it becomes a sort of generator of a deterministic dynamics. So this should indicate, if you think of heat operator, that the heat operator for LB, the heat tends to propagate more and more along the trajectories corresponding to y d over dx, which are precisely the geodesics in S1. So we will just explain now a little trick from algebra, which will allow us to eliminate the spurious part of the spectrum n over b squared, except for the eigenvalue corresponding to 0. So we just doubled the dimension of the space. Well, I will just say it in this way. I introduce the exterior algebra of R. Well, if you don't know what the exterior algebra is, just think of R plus R. And I will now make my operator LB, instead of being a scalar operator, I make it a matrix operator. So on the first copy of R, it is just the operator LB. And on the second copy of R, it is LB plus 1 over b squared. There is this operator n here, which is 0 in the first copy, and 1 on the second copy. So the effect of this is just to shift a little bit the spectrum. And what you discover is the following formula. That's just a consequence, easy consequence of what I said before, that the trace of the original heat kernel on S1, the original elliptic heat kernel, is given by TRS, that the difference of traces on the piece corresponding to n equals 0 on the first copy minus a trace on the second copy. This is just an elementary consequence of what I said before on the spectrum. So you see there is this fantastic quantity which is preserved, which is a trace of the original heat kernel. So that by making B tend to infinity in this context, because the right-hand side in some sense resembles more and more the geodesic flow, you recover the so-called Poisson formula for the heat kernel by an interpolation argument, by the interpolation between the original heat kernel and the geodesic flow. So let me now move to Selberg's trace formula. So let me just briefly explain what is Selberg's trace formula. So I give myself X to be a Riemann surface of constant curvature. I should say here of constant negative scalar curvature. So I then introduce the closed geodesics on this Riemann surface, and I call L gamma to be the length of a closed geodesic gamma. So what is Selberg's trace formula? It's a sort of generalized version of Poisson formula. So it just says that the trace of the original heat kernel on the manifold X can be expressed as an infinite sum. This infinite sum is actually essentially a sum over closed geodesics with complicated contributions. I will not just say them in words. There is just, first of all, a contribution from the trivial closed geodesics, from the points that's given here. It's given by a complicated integral over R, and then there is a discrete sum. Now, you see on the left-hand side, you have the heat kernel on the manifold, and on the right-hand side, you have something concerned with geodesics. However, the hypoelliptic theory, its purpose in some sense, is precisely to interpolate between the Laplacian and the geodesic flow. And so I will just briefly explain how to devise a tool which will allow us to obtain such a formula by interpolation. So a proof of this formula via the hypoelliptic Laplacian. So of course it gives much more. The proof gives much more than the case of Riemann surfaces. It gives basically the case of all possible compact locally symmetric spaces with an explicit formula which actually was not known. So let me again consider the case of my Riemann surface. So I told you before that the hypoelliptic Laplacian is an operator acting on a bigger space, which is a total space of the tangent bundle. So in this case, it is acting on a bigger space than that. So the bundle that you have to introduce is three-dimensional instead of being two-dimensional. And so this operator LBX, such that as in the case of S1, exactly as in the case of S1, the trace of the heat kernel is given by the supertrace of the heat kernel of this bigger, on this bigger space with this bigger hypoelliptic operator. So when B tends to infinity, when obtain a Zelbach-like formula for all so-called compact locally symmetric spaces by interpolation. So let me just show to you the formula for LBX. So in the case of Riemann surface, again, it acts on a bigger bundle. There is not just only the tangent bundle, but this does not matter. So I wrote here the formula for this operator LBX. You see that there is again the harmonic oscillator in the fiber direction, and there is these two things in red, the harmonic oscillator, and there is the geodesic floor. So it's again a hypoelliptic-like Laplacian. It has exactly the preferred structure. However, there is a catch here. There is an extra potential, which is a quartic potential. Unfortunately, harmonic oscillators are not enough. You need to introduce potential of degree 4 in the fiber variables. And of course, there are all these terms here, which are matrix terms that I will not explain. So such an operator, again, does not look at all like the original Laplacian on the base. However, what I'm saying is that essentially as B tends to 0, this operator deforms up to a constant, the original Laplacian on the base, and it has exactly formally the same properties as in the case of S1. So let me now explain connection with physics. So, okay, I hope that this is going to work here. Maybe this is not going to work. Ah, so there is an image to be shown. I don't know, maybe with a computer it will work. You have to click in the middle of the image. Yes. Yes, yes, you say, okay, you trust it. Yes, you have to trust it. Yes. Okay, so click again, if you can click. You say, okay. Ha. Click. Ah, what does it say? Okay, so there is a movie. No, maybe it's not going to work. I think, okay. So actually, I was visiting Courant Institute, and there was a place where people were doing gym. And they were using a machine called a treadmill. So I don't know if you know this sort of machine in which you run, and people run on this thing, and they actually run and they don't move. So this is typical of dynamics or heat operation in some sense taking place in the fibers of a vector bundle, all these machines being a sort of copies of the tangent bundle to the Earth, with people activating themselves without actually doing any real motion. You have even other machines called elliptical machines, in which the motion of the person is slightly more involved, but still the result is that all the energy is spent without any effective motion. And so you have to make this thought experiment of taking this rotating machine that you may have seen and just making it adhere to the Earth. At the point where it adheres to the Earth, the person, instead of just dissipating energy on the tangent bundle, starts effectively running. He may even have a chance of losing some weight. And when his mass gets very, very small, it starts being shocked by the shock of gas particles. So its trajectories become more and more erratic. until the point where his mass is almost zero or vanishes, where it becomes Brownian motion. So that's a way of describing, in some sense, the interpolation from the reverse side, starting from the motion in the fiber where people activate themselves without moving to the point where they become Brownian motion. Okay, so the Langevin equation now. So Langevin tried to reconcile Newton's law with Brownian motion. So the problem is that Langevin was aware, in spite of the fact that the trajectories of Brownian motion were not fully understood, that the trajectories in Brownian motion, for whatever that meant, had infinite speed. And so if they have infinite speed, if they have non-zero mass, they would have infinite energy, and so they are forced, in some sense, to have zero mass. So he tried to introduce an equation where, in effect, you could describe a sort of statistical physics for particles without a mass. And so Langevin equation that I will show you in the original form later on is exactly the equation mx double dot equal minus x dot plus w dot. That's an equation in R3, I should say, instead of R4. So for m equals 0, you recover equation of Brownian motion, and of course, for m equals infinity, you get the equation of geodesics, x double dot equals 0. So of course, Langevin certainly, I mean, his purpose was again physics, and he had certainly no idea of interpolating between two gadgets, and certainly not the idea that there would be conserved quantities. However, what we observe is that if we make m equals b squared, the hypoelliptic Laplacian, in some sense, describes the dynamics of the Langevin equation in a geometric context. So that's exactly the same equation. Again, my point is that this deformation preserves spectral quantities, which of course did not interest Langevin at the time. So here is Langevin compte rendu note. That's a note of 1908. Here's a Langevin equation here, and in which the white noise is described as the complementary force x, of which we know that it is indifferently positive or negative, and its size is such that it maintains the agitation of the particle, which without it, the viscous resistance would end up stopping it. So his point of view was completely mechanical, statistical physics. The fact that I introduced this equation has nothing to do with that. I was really interested in trying to find an interpolation which would preserve certain basic quantities that I hoped would be preserved, and I came out exactly to the same equation in some sense by case. But this just testifies to the fact that if we want to do something, since the objects which are at our disposal, like geometric or analytic objects, are limited, we end up finding exactly the same objects. So welcome to the role of mass in classical mathematics, and here is a short bibliography. Thank you very much.
Okay, thank you for your talk. Are there questions or comments?
Thank you. Could you please return to your slide number 16?
The slide number 16, okay. Sorry, it's a bit slow. Yes.
Yeah, thank you. Could you explain why you have y over b there?
So why do you scale y over b?
Exactly. So you said b is related to the math. So can you explain a bit more?
Yes.
Thank you.
So, okay. So I will describe this from a dynamical point of view. So when you make the convergence b tend to 0, okay, I will just explain this dynamically. So you have this family of diffusions of random passes which have finite speed. So when b tends to 0, the speed becomes infinite. So the speed explodes. In some sense, as we know, Brownian motion doesn't have a speed. So if we were not scaling properly y, which in some sense represents the speed, we'll just have something which blows up. So that's why we have, in some sense, you see, if you make x dot equals y over b, that means that y is equal to b times x dot. Yes? I told you b times x dot when b tends to 0. X dot itself tends to infinity because it becomes Brownian motion. But b times x dot, pointwise, behaves like a Gaussian, tends to behave like a Gaussian. So this is why we have to scale the coordinate y. If we are not doing that, everything would blow up. We would not have a limit. Okay? That's exactly to take into account the fact that the speed of Brownian motion explodes. So we have, in some sense, in this context, to renormalize it. So you might say, but you're talking about a variational problem. I told you in the case of Rn, the variational problem is directly connected with the heat kernel. If you have a Gaussian process, if you to compute the heat kernel, you as well can compute the minimum of the action, and you get the formula for the heat kernel. So all these things are completely related in the case of flat space. Looking at variational problem and looking at the behavior of the heat kernel, that is the behavior of Brownian motion. Okay, so that's the reason why the scaling comes in.
So you're saying that divided by b is exactly the right scaling, and if you divide it by b squared,
yes, if you were doing by b squared, it will all be, I mean, you want to get something from a variational point of view. Okay, that's maybe you have to make an experiment. Okay, in this case, you can compute everything. So there are explicit formulas for everything, and then you check that you have to do that. But the conceptual explanation from a dynamical point of view is that as this process, which is a Markov diffusion of bigger space, collapses in the proper sense to the base Brownian motion, collapse, what does this mean? You have a Markov of big space, and in the end, when b is equal to 0, it's Markov of a small space. So what has happened to this extra coordinate? Okay, that's always the question which is underlying this. So what has happened is that it has become effectively infinite, distributed everywhere. So, you know, we try exactly to describe analytically this phenomenon by which the extra coordinates are just disappear. And in other words, what we're describing is some concentration of the total L2 space of the fiber to the Gaussian function on the zero eigenvalue for the zero eigenvector of the harmonic oscillator. So that's a complicated, it's a messy thing, okay? You're absolutely right to ask the question.
And sorry, and the t, so first you had t anything, and then you put t equal to 1. So
oh, yes. So, I mean, for any t, the t here doesn't matter. I just put t equals 1.
So t
maybe.
is the length of the loop.
Yes, t is just a time scale. Yes, it's just a time. So we certainly do not make t tend to 0. We do not make any uniformity statement as t tend to 0, because certainly the asymptotics then is not uniform in t. Okay, so t is not the right parameter of deformation. If you want to get something uniform, it's in parameter b.
Okay, any other question?
Do I understand you well that you could explain the action principle of classical mechanics as being a limit of a stochastic version of the variational principle?
I would not say that. I think that what I've talked about has very little to do with stochastic mechanics. It has more to do a priori with quantum mechanics. Okay, we want to think in some sense not of the heat kernel for the Laplacian, but more for the Schrödinger equation. Okay, that's what we would like to do. So, in some sense, what we're just saying is that we deform the heat operator, which is connected in a way by weak rotation to quantum mechanics. We deform it to a family of hypoelliptic operators, but we certainly do not claim that the dynamics we describe has anything to do with quantum dynamics. So if you just say that we deform the Brownian motion through the Langevin equation, this is what I said. But I just do not want to say that what I'm talking about has anything to do with things like Nelson's quantum mechanics, anything like this. That, it's not at all like saying there is a statistical physics representation of classical mechanics. Absolutely not. Okay, this is in some sense a very mathematical construction.
Okay.
So if I start with a graph instead of a manifold, I have a well-defined Laplace operator, which is the generator of the random walk on the graph, and I have a well-defined notion of geodesic, which is the shortest path between 2 points. So does your theory extend to that case?
Okay, your question is extremely interesting because I gave a lecture 1 week ago and I had exactly the same question. Okay, and the words were exactly the same. So that's an obvious natural question, okay. So, I mean, obviously, we have used very much the fact that we are on a smooth manifold, we've used implicitly all the formalism of classical mechanics, the Lagrangian formalism, the Hamilton-Lagrangian correspondence, the symplectic structure, all of this implicitly comes in the construction. Now, what you're asking me is to say, if I take a space, which is essentially like a discrete space, maybe with this graph connecting the points, can you make a similar construction while not having the machine, like classical mechanics, Hamilton and Lagrangian correspondence, and so on? So, when you ask this question, I think you have the elements to answer it, because they are prior, in some sense, to asking if I can extend the construction. Okay, you must ask yourself, can I do variational methods? Do we have the notion of the energy? Do I have the notion of geodesics? Of course, some of these questions have positive answers, and you know them well. So they have positive answers. The question of knowing, can we go one step further? That is to say, can I make the graph bigger? In some sense, that would mean extend, adding an extra graph, building over a graph, an extra graph containing extra data, to which, first of all, the formalism of classical mechanics would adapt, maybe not exactly the same way. That's a preliminary question. And then there is a chance that maybe I could give the answer, which for the moment, I would say no. I don't want to verge on the positive side. I would say a priori no, but maybe yes. Okay. So I think that's a very, very good question. How to extend this formalism to discrete-like space. There are many reasons for trying to do that. I don't have a definite answer, but I think the preliminary thing is that on the base of all of this, there is classical mechanics constructions. And I don't know to what extent this formalism, the Hamiltonian Lagrangian formalism and so on, can be adapted. This I don't know.
Thank you very much.
Thank you.